Alright, in the previous lecture we have learned common operations like creation of heap, pick method in heap, size of heap, and level order traversal in heap. So hopefully everything is clear about common operations on heap. Now in this lecture, let's look at how can we insert a node in binary heap. Now let's say we have a binary heap like this, which is minimum heap. So here you can easily see that the root is less than its children, and it continues like this for all subtrees over here. So we want to insert, for example, 1 to this binary heap over here. Now the first step over here is we need to find a vacant place. So this means that we need to find unused cell in this array over here and a vacant place in this binary heap over here. Now if you look at this binary heap over here, according to the property of the binary heap, we said that all level must be full except last level. But in this case, in the last level, all elements have to be located as left as possible. So here you can see that in the first level we have all elements, and the second level also full, and the third level also full. So this means that we can insert this element at the fourth level as a left child of 30 over here. So this means that this is a vacant place in this case over here. And this means that when we are inserting this one over here, it's going to be inserted this empty cell over here. So as you can see in this array, the index of 8 is empty. So this means that we are going to insert this one to this empty cell over here. Now after inserting this one over here, we can easily see that we have a problem over here, which means that in case of binary heap, as we said, this is a minimum heap. So in case of minimum heap, the minimum heap property is violated, which says that the root node has to be less than its children. So in this case, if we check this root node over here, we can see that 30 is greater than 1. So this means that the property is violated. Now for these purposes, we are going to create heapify method, which is responsible for maintaining the properties of binary heap. Now in this case, we are going to heapify method for this node over here. In this case, it means that we are going to replace them. So we are going to check that if this node is greater than its root, it means that we have to swap them. So after calling heapify method for these nodes over here recursively, it's going to be like this. So 1 will be replaced with 30, which is its parent. So now in this case, you see that 1 becomes parent's parent. So in this case, 1's parent becomes child of its child. So here also, in this array also, it's going to be replaced with 30 over here. So it comes to the place of 30 and 30 comes to the place of 1 over here. Now after doing so, one more time, we are checking that if this value is less than its root, so here again you can see that 1 is less than 10. So this means that here again the property of minimum heap is violated. So this means that we are going to swap these values over here. So when we swap these values in heap 3 over here, it's going to swap in this array over here. So as you can see, as a next step, we are going to swap them. Then these values will be swapped from this array over here. Now one more time, when we reach the next step, in the next step we see that 1 is again less than its parent. So this means that we have to swap them. So we are going to swap them one more time. And when we are swapping it, it's going to come to the place of 5 over here. Now after swapping, if we check that, we can see that all parents are less than their children. So this means that the main property of binary heap, which says that in case of minimum heap, the parent should be less than its children. So this means that the main property is maintained. Now by doing heapify method after insertion, we are maintaining the property of binary heap. So this is how we insert a node to the binary heap. Basically what we did over here is, first we find the first vacant place for addition, then we did some adjustments to maintain the property of binary heap. Now based on this logic over here, let's create an insertion method for binary heap. Now here inside binary heap class, before creating the insert method, first I'm going to create helper method, which is heapify method. So in this case, we are going to create 2 heapify method over here, first for insertion and the next one will be for deleting. Now in this lecture we are creating insertion method, so that's why the first heapify method that I'm going to create will be for insertion. Now in case of insertion, when we are inserting an element to the binary heap, in this case we are always inserting the new element at the bottom of the binary heap. So this means that in this case our heapify method will be bottom to top. So because we are calling for the bottom element, then we are replacing it with the top elements if the property is not maintained. So here method will be like this: public void. So I'm going to name method heapify bottom to top. Now this method will take 2 parameters. The first parameter will be the index of node and the second parameter will be the type of heap. Because in this case, if the type of minimum, we have to maintain the property that root node is less than its children, but if the type is maximum, in this case we have to maintain the property that root node is greater than its children. So that's why based on this heap type, we are going to identify the condition. So the first parameter will be the index, and the second parameter will be the type of string, which will be heap type. Now after doing so, the first thing that we are going to do, we need to find the index of parent of this node over here. Now we know that when we have implemented binary heap in case of array implementation, we are calculating the children's index based on the parent index. So we are multiplying parent index by 2, we are getting the children's index. In this case, if I divide this index by 2, in this case I'm going to get the parent index of this child over here. So that's why I'm going to create new variable over here, which will be the parent, and I'm going to set it index divided by 2. So with this, we are finding the parent index for this index that we are getting as a parameter. Now then, the next thing that I'm going to do, we are going to check that if index is less than 1, in this case we are going to return. This means that we are at the root of 3, so we don't need to call heapify method anymore. So that's why we are going to return. So I'm going to put it like this: if index is less than 1 or equal to 1, in this case we are going to return, because in this case we know that the root node is always located at the index of 1, so in this case we have to stop over here. So this is our base condition. Now the next thing that I'm going to do, I'm going to check the type of the heap. So if heap type is equal to minimum, in this case the root node has to be less than its children. So in this case we are going to check that if the current value is smaller than its parent, then in this case we are going to swap them. So in this case I'm going to write if condition like this: if ARR in the index we have current value is less than ARR, the value of the parent, so in this case we are going to use the parent index over here, then in this case we have to swap them. Now to swap them, I'm going to create a temporary variable over here, so in which we will have the value of the current node. So I'm going to set it like this, index, then I'm going to set this current value, the value of its parent, so it's going to be like this: ARR with index is equal to ARR with parent index. Then we are going to do set to the parent the temporary value that we have created over here. So it's going to be like this, is equal to, should be temp. So now with this case, we have successfully swapped the child's value with the parent value. So in this case, we have maintained the property of binary heap for minimum heap, in which it says that children's value has to be less than parent's value. So we are swapping them if this is the case. Now otherwise, we are going to check it for maximum heaps. Outside this if condition, we are going to write this: else if heap type is equal to max. In this case it means that this maximum heap, so in this case the condition will be changed. So I'm just going to copy this line of code from here, because basically it's same, but here we are going to check that if the children is greater than its parent, in this case we are going to swap them, because parent has to be the greater in case of maximum heap. So that's why we are going to swap them. Now at the end, we are going to call this heapify method recursively for all nodes over here, because we have to check for all subtrees over here. So that's why we have to call heapify method from bottom to top with the index of parent, because in this case we have checked this child and continue to the parent. So in this case it's going to continue to its parent and to its parent until we reach the root node. So that's why we are going to call for parent value over here. Now with this, we have successfully created heapify method for bottom to top in case of insertion. Now before continuing to the insert method, let's see what's the time and space complexity for this method over here. Now we are going to start from the first line of code. So in the first line, we are calculating the parent index. So this one takes a 1 time complexity. Then in the if condition, we are checking that if the index is less than 1, we are returning. So this one also will take a 1 time complexity. Then we are continuing to the next if condition. Now in the next if condition, we are checking that if heap type is minimum, we are doing some swap operation over here. So this will take a 1 time complexity. Then in the next line of code, we have if the current value is less than the its parent's value. In this case, we are doing swap operation over here. So you can see that these are simple assignment statements. So this means that this inside if condition will take a 1 time complexity. Now in the else if condition, we are checking that if heap type is maximum, then in this case we are doing also swap operation over here. So this one also will take a 1 time complexity. When we continue to the last line, in the last line we are calling this method recursively. So this means that we are calling this method recursively for only the parents. So that's why it will take all again time complexity. If we combine all these complexities over here, we will get all again time complexity. Now the space complexity is also all again, because in this case, whenever we are calling a method recursively, we are inserting elements to the stack memory, so that's why the space complexity is also all again. Now with this, we have successfully completed a heapify bottom to top method. Now let's continue to create our insert method in binary heap using this heapify method. So I'm going to declare insert method over here. So it's going to be like this: public void insert. So this method will take two parameters. The first parameter, the value, will be the value that we want to insert to our binary heap, and the second parameter will be type of heap. So we need type of heap over here as well, because based on the type we are going to do some swap operation over here. Now the first thing that we are going to do over here, we are going to insert this value to the next vacant place. So we know that if we use the size of 3, in this case we are accessing the last element in the array that we have created over here. So if I put size plus 1, we are going to insert this value to the next vacant place. So in this case it's going to be like this: ARR size of 3 plus 1 is equal to value. Then we are going to increase the size of 3 by 1, because in this case we have inserted one element to this tree over here. Then after doing so, we are going to call heapify method to check that if the property of heap, binary heap, is maintained or not. So as I mentioned, in case of insertion we are calling heapify bottom to top, so that's why I'm just going to call it heapify bottom to top. As an index I'm going to take the size of 3, because in this case in the size of 3 we have the element that we have inserted over here, because after insertion we are increasing the size of 3 over here. Then we are going to call it for the heap type that we have inserted from the parameter over here. Now after doing so, I'm going to print out to the console saying that the value is inserted. So it's going to be like this. I'm going to put the message like this: insert. So let's concatenate with the value successfully in heap. Now after doing so, let's see how this is working in practice. So here inside main class, I'm just going to insert some elements to this binary heap over here. Then I'm going to call level order traversal to see that if the property of the binary heap is maintained or not. Now in this case, I'm going to do it like this: new binary heap. So let's call insert method. So let's first, for example, insert 10. Then I'm going to insert it for example, minimum type. Then after 10, I'm just going to insert 5 over here. Then I'm going to insert 15. Then for example, I'm going to insert one more time 1 over here. So the last insertion should be the root node of this binary heap over here. So let's run our code. Now after running, you see that it says that the 10 successfully inserted in the heap, then 5, then 15, then 1. Now when we are running level order traversal, we see that first it's printing out the root node, which is 1, but we have inserted the 1 at the end. So it becomes the root node of this binary heap over here after heapify method. Then it's printing out 15, which is left and right child, and the left child of 5 is 10. So in this case, you see that 10 is less than its parent, so everything is maintained over here. Now if I change this one to maximum, all elements over here to maximum, in this case you will see that the order is changed. So if I run it like this, so the root node should be 15 over here. Now after insertion, if I call level order traversal, you see that the root node becomes the 15, then the left child is 5 and the right child is 10, and the 5's left child is 1. So maximum heap property, which says that parent has to be greater than its children, is maintained over here. So as you can see, our insertion method works the way that we want. So in this case, we have successfully created insert method for binary heap over here. Now let's see what's the time and space complexity for this insertion over here. So here again, we are going to start from the first line of code. So in the first line, we are just updating the value of cell in the array. So this will take O1 time complexity. Then we are increasing the size of 3. So this one also will take O1 time complexity. Now we know that heapify bottom to top method will take O again time complexity. Then at the end, we are printing out message to the console saying that inserted successfully. So this one also will take O1 time complexity. Now if you combine all these complexities over here, insertion method for binary heap will take O again time complexity. Now similarly, the space complexity is O again, because in this case, when we are calling heapify method, this method calls itself recursively. So that's why it takes O again space complexity. Now with this, we have come to the end of this lecture. So in this lecture, we have implemented the logic for inserting a node to the binary heap. So when we are inserting a node to the binary heap, it might cause violation of the binary heap properties. So by calling heapify method, we are maintaining the properties of binary heap. So hopefully everything is clear about this lecture. Now see you in the next lecture.